So in the last video, we took a look at the important theorem for this section, which was L'Hopital's rule. And it said that if I had two differentiable functions, where the derivative of g was not 0, then if I was taking a limit of one function divided by another, and when I did direct substitution, I ended up with one of the following indeterminate forms, then it would be the case that the limit that I was working with would be equal to this new limit. That is, both limits would produce the exact same answer. Now we're going to go ahead in this video and attempt to try to justify, at least partially, why in the world we could state with any certainty that these limits have the same answer. So proving L'Hopital's rule in general is a little bit complicated and goes slightly beyond the scope of our course, at least in that it's going to introduce a lot of additional ideas that we have not yet justified. So what we're going to focus on here is just the proof of a special case. If you're interested in the full proof, you'd like to kind of have all the details, I'd be happy to talk to you about that during office hours. So let's take a look here really quickly at the proof of a special case. And I'll start us off by kind of at least highlighting what's going to be special about this particular case. So first off, let's suppose that when we're working with the limit as x approaches a of f of x over g of x, that we find that this is in the indeterminate form. This is in the indeterminate form of 0 over 0. Okay, so let's assume that to start. So again, the rule up here generally states you could be in the form 0 over 0 or infinity over an infinity, but let's just assume for the moment that we have specifically this form. Now we're also going to make a big assumption here, and this is kind of our extra special assumption, that f prime and g prime are going to be continuous at x equals a. And of course, we'll assume, like we must, that g prime of x is not going to be equal to 0. That's one of our original given conditions. Okay, so this is what we're going to start with. And again, what you'll notice here is that this special case is really applying to the fact that we have this special indeterminate form and that our functions are continuous. The theorem above doesn't state that those things have to be the case, but if they are, we can prove this special instance. So let's go ahead and see what or how this works, and can we actually show these two limits are going to be the same. So with this information as kind of our givens at our beginning, we can see what we can start to determine from this. So first off, we could say that since it's the case that the limit of our f of x over our g of x is in the form 0 over 0, that obviously means that when we did a direct substitution, we got 0 on top and 0 on bottom. But then what that means is that when I plugged the value of a into my function f, I got back 0. And when I plugged the value of a into my function g, I got 0. So when I did direct substitution, I got 0 over 0. Okay. Well, I can go ahead now and note a couple other things. I can then easily state that, note that since f prime of x and g prime of x are continuous at x equals a, that's what we're starting with up here, then I can state that this means that regular f and regular g, notice if they're continuous at this value, then that means that they must be defined there, right? That means f prime of a has to actually exist and be equal to the limit of f prime of x as x goes towards a. It's just our basic limit, our definition of continuity. But if that derivative then exists at that point, I can say that the original functions are differentiable at x equals a. But of course, if they're differentiable at x equals a, I can say that they are going to be continuous at x equals a. So because I know that the first derivatives are continuous at a, I know that the original functions are differentiable there, and of course then also continuous there. Now, of course, what this means is the following. Since I know that these functions are continuous there, I would definitely be able to state that my limit as x approaches a of f of x is going to be equal to f of a. And I can also state that the limit of g of x as x approaches a should be equal to g of a. Right? Like that's what it means for these functions to be continuous at a. But since I'm already told up here that f of a is equal to 0, since we already deduced that, and g of a is equal to 0, I can claim that all of these things then are equal to 0. Well, when I put all of this together, let's take a look at what we can say. So I'll say, now we can say that. And again, keep in mind what we're going to try to figure out. We want to determine if, based off this information up here, we can show that these two limits would be equal to each other. That is, they produce the same answer. So we started off with supposing we added this indeterminate form, supposing that our derivatives were continuous at a value, and then we just deduced some other facts from that. So now we're going to go ahead and actually try to see what is going to be the value of our derivative, or of our limit that has our derivative functions in it. I want to figure out what this is equal to. What I'm hoping is that by the time I get all the way to the other end, that I can show that this limit here will have been equal to this limit right here. Now, if we were to go ahead and actually take a look at this, I could note that first, I could apply some limit laws. That is, I could take the limit of the top and the limit of the bottom. And since I know that these functions are continuous at the value of a, then I know that when I do the limit of this function, that's just going to be equal to being able to just do a direct substitution. If they're continuous, I can direct substitute. Okay, so this is great right here. I can say that f prime of a over g prime of a. But wait a minute. If I do f prime of a, I know that that's the derivative of the function evaluated at a, and I know that I could go back and actually use my definition of the derivative to rewrite this. Now remember that our definition of the derivative used to be something like f of x plus h minus f of x all over h. All right, and then we had a limit as h went to 0. But there was another form. That was f of x minus f of a over x minus a. Notice this is still a slope formula in here, change in y over change in x, and I'm pushing one of the x values towards the other. So down here in the denominator, I'd have the same thing. I'd have g of x minus g of a all over x minus a. So again, I'm just rewriting what the derivative looks like. Now, since I have a limit of the top and the bottom here, I could rewrite this as just one giant limit of the entire kind of fractions that I have listed out here. So I could rewrite this one more time to look like the following. So g of x minus g of a, x minus a. Now, of course, I'll notice that I have two fractions here being divided, and so I could multiply by the reciprocal. Now, when I do that, I'll be able to see that these x minus a's are going to be able to cancel out, and I'm going to be left with a limit, as x approaches a, of f of x minus f of a all over g of x minus g of a. And now I can go ahead and actually think about what this looks like one more time. Because actually, what is f of a the same as according to what we deduced from up above? Well, f of a is actually equal to 0, and so is g of a. And so this would actually simplify down to just be the limit as x approaches a. In the numerator, I would just have f of x, and in the denominator, I would just have g of x. And notice that what we've said is that the limit with the derivatives is equal to the limit with the original functions. Now, this here would completely conclude this special case of the argument. Now, again, it's important to note here that all we've really shown is that these two limits are going to be equal in this specific special case. But if we we should recognize here that this applies to not only the special case, but to all the cases outlined here in the theorem box above. And again, if you're interested in seeing the proof that covers all the different cases, I'd be happy to kind of go over that with you. Hopefully, though, this gives you some sense of how exactly we might actually know that this is true. And now the only question is, how do we actually put it to use? And we'll cover that in the remaining videos.